A pleasant morning to everyone. I am Rebecca Alyanna Gadia,
And I'm Maria Aira Calma.
and together we will be presenting our thesis paper entitled Determination of Photon Shielding Features of Composite Concretes with Varying Concentrations of Volcanic Ash and Face Masks as Aggregates via simulations under the supervision of Dr. Astronomo and Dr. Caparanga.
The applications of nuclear radiation extends to agriculture, medicine, and other industries. However, we can still experience adverse health effects due to prolonged or overexposure to photon radiation, due to its penetrating power. With this, the photon shielding characteristics of materials are examined to attenuate photon radiation. This can be done by evaluating the interaction of photon with matter.
Previous studies have investigated various materials for photon shielding, such as soils, ceramics, polymers, glass systems, and concrete systems. However, there are no data yet on photon shielding features of composite concrete with volcanic ash and face masks, nor concretes with both volcanic ash and face masks. Additionally, the study also utilized EPIXS, a new software developed by the PNRI for the determination of photon shielding features.
The main objective of the study is to investigate the photon shielding features of concrete with partial replacement of volcanic ash and face masks in its fine and coarse aggregates, respectively.
The specific objectives of the study are to determine the photon shielding parameters of concretes with volcanic ash and face mask filters as aggregates at varying concentrations, to determine the theoretical photon shielding parameters of the material using WIN-XCOM, PXPSD, EPIXS, and Monte Carlo simulations. Among these programs, only EPIXS used EPIX 2017, the most updated photoatomic library. With this, our last objective is to ascertain the differences of the data obtained from each photoatomic library.
This study will have contributions to gamma shielding applications such as in medical and research facilities, due to its economic and environmental advantages over other shielding materials. It has also been proven by previous studies that concrete with plastic wastes and volcanic ash are comparable to standard concrete. Recycling the masks and volcanic ashes will also be beneficial to reduce wastes.
The study will only include the parameters shown in the slide. Because of the restriction due to the pandemic, the chemical composition of the proposed material will only be based on the data obtained from previous studies.
The photon attenuation parameters of a material will determine its capability for photon shielding. The parameters are the mass attenuation coefficient, mean free path, half-value layer, effective atomic number, effective electron density, and energy and exposure buildup factors.
In light of the prevalent use of face masks, Phil Martin Lynch and others investigated the mechanical properties of concrete with face masks. Results showed that increasing the face mask in the concrete mix will increase the compressive and tensile strength of the concrete. However, this is only advantageous up to 0.2% as there was an observed decrease in the strength beyond 0.2% face mask.
A study by Diff and others discovered that adding about 20% volcanic ash as partial replacement to concrete materials exhibited the nearest compressive strength to the reference concrete, while it has the highest strength gain for the period of 28 days. This increase in compressive strength can be attributed to the delayed pozzolanic reaction of pozzolan with cement hydrates, forming calcium silicate hydrates, which acts as binder.
The material compositions and densities were obtained from previous studies and were calculated as shown in tables 1 to 5.
The parameters previously discussed was determined using the following simulation programs: WinXCOM, PXPSD, EPIXS, and Monte Carlo simulations. The photoatomic library used by WinXCOM and PXPSD is XCOM, EPIX 2017 for EPIXS, and EPDL97 for MCNP5 code.
For the present study, the MC simulation utilizes the needle-thin cylinder model as shown in the slide. The simulation was done using MCNP5 code, which uses EPDL97 as the library. Considering that the model demonstrates a true narrow beam geometry, the number of incident and emergent photons can be related by the Beer-Lambert law, where the mu or the linear attenuation coefficient can be calculated. The mu is related to the mass attenuation coefficient, which is to be discussed in the following slides.
The mass attenuation coefficient can be calculated by dividing the linear attenuation coefficient by the density of the material. The half-value layer can be calculated by dividing the natural logarithm of 2 to the linear attenuation coefficient.
Similarly, the MFP can be calculated from the inverse value of the mu. On the other hand, the ZF can be calculated by dividing the total atomic cross-section by the electronic cross-section.
The effective atomic density can be obtained by multiplying the effective atomic number to the ratio of the Avogadro's number to the summation of the atomic fraction times the atomic mass of an element.
Three cases were investigated, namely increasing volcanic ash composition, increasing face mass composition, and increasing both the volcanic ash and the face mass composition. The obtained data for each case was compared to the reference concrete CF00V05 by using percent difference. The libraries XCOM and EPDL97 were likewise investigated of their percent difference from the latest library, EPICS 2017.
A sensitivity analysis was done using the one factor at a time method to the reference concrete to determine the sensitivity of results to the elemental composition inputs obtained from previous studies. The composition of lime, iron oxide, and potassium oxide in fine and coarse aggregates was varied an increment of plus and minus 20% of their original value. These compounds were chosen because calcium, iron, and potassium have the highest atomic numbers and are expected to have the greatest impact on the MAC of the material.
Now we will present the parameters obtained from EPIXs, starting off with the MAC. The graphs in the first row are the MAC values for cases 1 to 3, from left to right plotted against the energy in kilo-electron volts. These plots tell us that the samples are more advantageous in low-energy applications because of the high MAC values. But since all plot lines are almost coinciding with each other, the percent difference was obtained as shown in the second row. For case 1, the percent difference is only apparent in low energies, where CF00V05 is the most beneficial sample as it has the highest MAC values. For case 2, there is an inverse trend between energies at low and high energies. Therefore, increasing the phase mass composition will be favorable for high energy applications. Lastly, for the third case, the similar trend with case 1 can be observed because the sample's volume contains up to 20% of volcanic ash, whereas the face mass is only up to 0.20% of the total volume. The trend and scale of the MAC values are found to be consistent with previous studies of normal weight concrete by Un and others, composite concretes with metal oxides by Tekin and others, and composite concrete with perlite materials by Agar and others.
For the MFP, a low value is more desired since it denotes the average distance traveled by a photon before its first interaction. The MFP of the samples at all cases have a small percent deviation from the reference concrete CF00V00 shown at the second row of the graphs. Also, similar to MAC, the MFP values of samples CF00V05 and CF05V05 are more advantageous below 300 kV, while the samples CF00V20 and CF20V20 are more advantageous beyond 300 kV. Since the volcanic ash contributes more to the concrete mix than the face mass, increasing both their compositions up to 0.20% face mass and 20% volcanic ash showed an advantage at the high energy region. Next is the HVL. Since HVL is indirectly proportional to MAC, lower values of HVL are desired for photon shielding applications. As previously explained, cases 1 and 3 depict similar graphs as volcanic ash replacement is more prevalent in volume compared to the face masks. This means that adding face masks to the concrete mix have a negligible effect on the HVL. This result denotes that increasing the face mask composition in the concrete does not significantly affect the photon shielding capacity of the material, while the mechanical properties are improved in terms of compressive and tensile strength.
Conversely, the ZF values are highest at low energies for all cases and constant beyond 300 kilo-electron volts. The high ZF is caused by the photoelectric interaction dominant at low energies, whereas the constant ZF values is caused by the pair production interaction at high energies. Comparing cases 1 and 2, it can be observed that incorporation of face mask has negligible effects to the effective atomic number, whereas volcanic ash have a negative correlation to the ZF. Likewise, the same conclusion can be said with case 3. Nonetheless, the results were comparable to the various rocks as previously investigated by Obaid and others in 2018. Similarly, there were no observed significant differences for NF at energies beyond 300 kiloelectron volts for all cases. However, at low energies, a high value of NF can be observed, thereby it can be concluded that the material is advantageous at low energies.
The exposure buildup factor of sample CF05B00 at different values of mean free path was obtained. Based on graph A, it can be observed that at all MFPs, the values of EBF at low energies are low, subsequently peaked at about 400 kiloelectron volts, and then went down as the energy increased. These three phenomena can be attributed to the photon interaction dominant at each energy range, namely photoelectric absorption at low energies, Compton scattering at intermediate energies, and pair production at high energies. The behavior of the EABF response at varying MFPs is also almost similar to the EBF response as the photon energy increases. Moreover, an increase in the MFP causes an increase in the EABF and EBF values because the latter is in direct proportion with the scattering volume. In this case, the photon scattering interactions will be more likely to occur, increasing the EABF and EBF values.
Because of the various compounds present in the aggregates, a sensitivity analysis was done to determine which compound greatly contributes to the MAC of the sample. The compounds lime, iron oxide, and potassium oxide in coarse and fine aggregates were investigated, and its variation rates and sensitivity indices are shown in the slide. As expected in both parameters, iron oxide had the highest impact on the MAC, mainly because of the potassium having the highest atomic number among all the input elements. Similarly, potassium oxide yielded the least effect among the three compounds because of the low atomic number of potassium compared to calcium and iron. Furthermore, varying the oxides and fine aggregates was found to be negligible, with the value of the potassium oxide being closest to zero. This is because fine aggregates have smaller weight percent in the total concrete mix compared to coarse aggregates.
To compare different libraries, the MAC values were also determined using other simulation programs, specifically WinXCOM, PXPSD, and MCNP5 from NC Simulations. This table summarizes the MAC values and the corresponding percent difference from EPIC's 2017 library. Based on this, the MCNP5 have the greatest number of best agreements with EPIC's 2017, as this method considers the geometry in the simulation. Furthermore, at certain energies, the data for WinXCOM and PXPSD have coinciding values, which is expected considering that both programs utilize the same photoatomic library. Aside from that, it is also worth noting that the values of the percent deviation ranges only from 0.01% to 0.32%.
After conducting the simulations and analysis of the data, several conclusions can be drawn from the study. The study used WinXCOM, PXPSD, FTXs, and Monte Carlo simulations to obtain the MAC values and other photon shielding parameters of the sample concrete. The MAC values of the concrete samples exhibit minor deviations from the reference concrete at energies beyond 300 kiloelectron volts. Based on the sensitivity analysis done using one factor at a time method, increasing the amount of iron oxide in the coarse aggregates have the most positive effect on the MAC of the reference concrete. Lastly, MAC values obtained from different photoatomic libraries, such as XCOM and EPDL97, have an insignificant deviation from EPIC's 2017, with 0.32% being the highest.
For future studies, it will be advantageous to investigate the mechanical properties of concrete, such as compressive, tensile, and bending strength, alongside the photon shielding parameters through experimentation. Measuring the actual elemental composition of the samples will also be helpful in the comparative analysis of experimental and analytical data. Investigating the trade-off between the mechanical and the photon shielding properties will further determine which component or element will be most influential. In light of the waste generated from the COVID-19 pandemic, examining the plastic composition from face shield as a possible replacement for coarse aggregates of the concrete will be environmentally and economically advantageous. However, it is also necessary to consider the disinfection of these wastes, as they are hazardous. It will also be better to consider concretes doped with various metals such as strontium, zirconium, as theoretically investigated by previous studies. This marks the end of our presentation. Thank you for listening.